In this video, we will examine length contraction. In part 4 of this series, we demonstrated how Einstein had alerted us to the possibility that the length of a body might change with motion. He had provided the example of a train traveling along an embankment with a velocity equal to v. He stated that the length of the train, as measured from the embankment, may be different from that obtained by measuring in the train itself. He followed this warning with the introduction of the Lorentz Transformation, which we will now use to examine Einstein's assertion. Einstein sets the scene by explaining his use of coordinate systems. He says that coordinate system K corresponds to the embankment, and coordinate system K1 corresponds to the train. He further explains that any event would be fixed in space with respect to the K coordinate system by the three perpendiculars x, y, z, and by a time value t. The same event would be fixed in respect of space and time by the corresponding values x1, y1, z1, t1 with respect to the K1 coordinate system. So when an event takes place and we know the values of x and t with respect to the K coordinate system, we use the Lorentz transformation to calculate the value of x1. And we use it to calculate the value of t1. So, having set the scene, Einstein returns to the subject matter of length. In section 12 of his book, he sets up another thought experiment. He says, I place a meter rod in the x1 axis of K1 in such a manner that one end, the beginning, coincides with the point x1 equals 0, whilst the other end, the end of the rod, coincides with the point x1 equals 1. He asks, what is the length of the meter rod relatively to the system K? In order to learn this, he tells us, we need only ask where the beginning of the rod and the end of the rod lie with respect to K at a particular time t of the system K. The length is then given by subtracting the beginning value from the end value. We're now in a position to make that calculation, but before doing so, it is convenient to establish some naming conventions. The beginning of the rod on the K1 system we will name x1a. The end of the rod we will name x1b. We will adopt a similar convention for the values on the K system. It is also useful to introduce a shorthand for the Lorentz factor. In the previous video, I explained that the factor, indicated by the arrows, performs the duty of limiting the relative velocity to the constant velocity of light in a vacuum. This factor is often named the Lorentz factor. And the common but not exclusive practice is to denote this function as gamma. And so we can write the Lorentz transformation like this. We will use this notation in the following calculations. x1a is equal to xa minus vt multiplied by gamma, and x1b is equal to xb minus vt multiplied by gamma. To find the lengths, we do as instructed by Einstein. We subtract x1a from x1b and perform the same subtraction on the right-hand side of the equations. We can simplify the right side because both components are multiplied by gamma. We now find that there is a minus vt and a plus vt on the right-hand side. So they cancel out and we are left with this result. We are looking to calculate the value of the x-coordinate system, So it is convenient to divide both sides of the equation by gamma, which gives this result, which in turn can be regarded as the generalized rule for the transformation of lengths. In all cases, the length of the moving system divided by gamma equals the length of the stationary system. To customize this equation to match the thought experiments provided by Einstein, we can further generalize and say that the length relative to the embankment k is equal to the length relative to the train k1 divided by gamma.